All right. Well, good morning, everybody. I'm going to go ahead and do our first lecture for Calc 2, just solo here. I will check the survey tonight to see when people want to do this. Let me just start in with a couple of things. If you're having trouble finding where the website is, let me go ahead and share you my screen, and then we'll get into the lecture and have that go. All right, so here's my screen. All right, so if we go to, so one thing I really don't like about this is I don't have a lot of real estate here. But if I go off to our class, okay, here's our course home. All right, if we go to coursework and hit content, all right, then you'll see all of this stuff, all these modules sitting here. You're going to go all the way down to the bottom where it says WebAssign. Wait, it didn't do anything. But it did. It's up here, okay? And you're going to go ahead and hit this one here, WebAssign. And yours is going to look a little different than mine because I got all the teacher stuff with all the different shell courses in it. But that's where it should take you to log in. And you should see a bunch of assignments here. And some of you have noted, said, hey, wait a minute, these are all due on the 14th. I'm like, well, sort of. Oh, this is your first test. If we go to future, then you can see that there's actually 3 sets of things to work on, okay? There's a chapter 7 review, a chapter 10 review, and a chapter 11 review. I counted those as the homework as well, so same thing with Calc 2 final exam. These are all homework stuff that sits there. I've got to set up the whole other thing going on here, but that's where everything is. All right, your ebook, that's going to be important. Okay, be able to read the book, but that's where everything is, and that's why it's laid out the way it is. All right, so you can see a little bit about what's going on here. Okay, so today we're just going to talk about areas between 2 curves, and I usually, we have a 4-credit class technically, and I just find it to be I think it's a little bit easier. It's a little bit more digestible to sit there and deal with maybe a 1-hour lecture rather than a 1.5-hour lecture twice a week. So we do. I do like Monday through Thursday, same time every day. Maybe 50 minutes, maybe an hour of demonstrations and lecture and stuff like that. So you're not required to attend them all. I just want to make that clear. Like you're not. I'm not taking attendance on this. All right. If you watch them, great. If you don't watch them, well, that's on you. There's other videos and there's other presenters that on YouTube that do a much better job than I do. So my feelings are not gonna be hurt. I know there are people that are more talented than I am. Okay, so why don't we stop this, and go to something where we could start dealing with a lecture type of a thing. And oh dear, where is there it is. Okay, so yeah, I've got a pen, I've got my little board here to write on, and we'll just go ahead and get into this. So this is the area between 2 curves. So the idea here, all right, is we're going to have some kind of a coordinate axis, and you're going to have like an f. Well, we'll do a little f of x, okay, and then we're going to do maybe a little g of x down here, okay, g of x. And the goal here is we're trying to figure out like what is, there we go, that's a nice bold color. What is the area between these 2 curves? Okay, and all we're going to do is we're going to take our f of x minus our g of x. All right, and then we have to get right, we have to get an area, so we're just going to integrate that. All right. The other thing is that your book wants to be clever, and they're going to do some kind of a curve this way, pretend that's a function, okay, in y, and they might have another curve sitting there like that. And all we're going to do is we're going to take the function on the right, so I'm just going to call that xr minus your function on the left. Okay, so we could have a an f of x here and a g of x here. And again, all we're going to do is take our f of x minus our g of x. Now, I never remembered this when I was taking the class, but what I did do is kind of like rotate this so it looked more like an xy coordinate graph. And since this one was on the top, it was this one minus that one. Okay, so you can just kind of tilt it in your head and kind of figure out which ones are which, and that might help a little bit as far as figuring out what goes, you know, what one goes on top and which one goes on the bottom. Your book likes doing this to you. I'm not particularly fond of doing this, but there are a couple of questions that deal with this. So let's just start going through this stuff. All right, I'm going to start off kind of on the easy one, and then we'll go and deal with the hard ones. Okay, so I often use books out of something called the Schwann's Outline. Right, just to give you another resource for this. I think it's over here, and yeah, I've got, oh no, wrong one. There we go. Schwann's Outline, just to give you an idea of what this thing is supposed to look like. See, Schwann's Outlines. If you've never heard of these are a fantastic resource because there's a lot of problems that are absolutely solved, and then you've got about 1,000 problems that are unsolved. And since this is calculus, this goes for three semesters. When I was an undergrad, when I was a grad student, I lived and died by these books. They just had a ton of extra problems in them, and they were really helpful. When I was going to school, these ran about $10. I think they've gone up in price since then, and I think they're now up to 15. So they might be a little bit higher. They might be at 20 now, but these are paperbacks, and I can't look at the back cover. But if you ever do have a physical copy of these, you look at the back cover. There is one for like every engineering class you would ever be interested in taking. There's one in every math class you would ever be interested in taking. I will warn you, these were written in the 60s, and some of the notation and some of the problems and some of the things they ask you to do reflect the fact that it was written in the 60s. So, you know, take with a little bit of salt, but I was taking one class, and you know, it was one of those classes where, you know, each problem takes about 3 hours to set up and do. And yeah, I found every problem he asked us in our Schwann's Outline. Okay, I'll tell you more about that later. But that's, you know, it's a really nice resource. I got through my physics 1 class using these things because you know, the book just didn't have as many problems, and they were not as good. So that's my other resource. All right. So that's where I got this problem. Find the area of the region bounded by the parabolas 6x minus x squared and y equals x squared minus 2x. So the first thing, it didn't give us like, what are the x's? So one of the things we might have to do, right, is figure out where the heck these things intersect. We also have to figure out, like, they didn't draw it for us, like which of these is on the top. All right, so we kind of have to get an idea. So my f of x, right, I'll just, right, this is 6x minus x squared. So we're going to go ahead and factor out an x, and we're going to say 6 minus x. All right, we'll say y1. And our y2 is equal to x squared minus 2x, right? You know what we like to do is that. And then y2 is equal to x minus 2. All right, so let's go ahead and do a little bit of a graph of these things, just to kind of get an idea of what's going on. It's clear that both of these start at 0, right? Both of these have an intercept at 0. This one has an intercept at 6, right? If I set this equal to 0, we get x equals 1, 2, 3, 4, 5, 6. And I'm looking at this parabola, and I think, oh, this opens down. So this parabola is going to do that. Do you know, there's another way of figuring out the vertex, and it's the average of the 2 intercepts, okay? And since my intercept is 0 and 6, we're going to be up here somewhere. So at x equals 3, that's where my vertex is. So I'm kind of sketching out a parabola here, sketching out a parabola there. All right, so that's one. Now, for the other one, right, this opens in the other direction, right? This is positive, so it opens up, and we're here, and we're at x equals 2. And again, I don't know how far down this is going to go, but I do know that the vertex is the average between 0 and 2, so we're at the average. Okay, so we're going to go down, and we're going to go up, right? And then we're going to have a parabola here, we're going to have a parabola there. Okay, I was going to say, you know, we invented Desmos for a reason, so pretend this is, oh, I don't want to do it that way, I want to do it this way. Okay, pretend that looks like a drawing, okay, of parabolas. So what we're trying to do here, all right, make this a little bit better to not interrupt my coordinate axis here. So what we're trying to do is we are trying to figure out what the heck is this area in here. Okay, don't worry, we're not going to be adding up little rectangles for all of these problems. Okay, I remember teaching Calc 1 and there's a lot of emphasis on rectangles, and I'm still a little ticked off about the fact that that's our standard now from the state. Like, why are we doing this? But this one, we're summing all of these up, but we're going to do it the fancy way. We're going to use integral. We're not going to sum up little boxes. All right, we'll get to enough of that a little bit later, but you know. So here we are, right? Which one is on top? Well, it looks like the parabola that's facing down is the one on top. Here's my f of x. This one, right, is the g of x. Now, the question we have here is, it just says bounded by. So what that means is, where's their intersection? Okay, well, one of them is we're going from 0. Where the heck is this? All right, so don't look at my graph to say, oh, it's 1, 2, no, don't do that. Okay, because my drawings are terrible. Anybody who's had me before will know drawings are the worst. So what we're going to do is we're going to set these two equal to each other. Okay, so we're going to go ahead and set 6x minus x squared is equal to, right, x squared minus 2x. We have to solve this. Okay, so I'm just going to put everything on one side of the equation. That's how we solve equations, right? Put everything on one side. So we have 2x squared minus 8x, and say that equals 0. Okay. Fortunately, we don't have a constant term. We don't have to deal with any quadratic formulas. Just to let you know how terrible this could be, right? There's all the fun things there. But we can just factor out a 2x, and then we have an x minus 4. Clearly, the intercept points are, right, the intersection points are x equals 0 and x equals 4. So my drawing wasn't too terrible. We have integral between 0 and 4. That's the region bounded by these two curves. Okay, like what about this part? Like, yeah, it's not bounded, so we don't have to worry about it. Okay, the part that's bounded is just in there. So we're going to integrate. Okay, and I promise I'll go slow because I'm just going to guess that you know, end of last semester doing Calc 1 integration tools. You probably haven't touched it since December. You'll get faster. I'll get faster. Okay, but we have, right, f of x minus g of x dx. My f of x was, right, 6x minus x squared. So this is, I'm sorry. Yeah, let's go ahead and erase that. So 6x minus x squared. Right, that was my f of x minus, and my g of x is what? My g of x is x squared minus 2x. So there's my f of x minus g of x. All right, and if you don't do this and you set it up this way, it is going to be a little bit weird. Okay, so here we go with all of this business. So we're going to have, this is equal to, right, this is equal to 0 to 4. And we're going to have negative x squared minus negative x squared. That's a negative 2x squared. Right? We have 6x minus positive, right, minus a negative. So we have a plus 8x, okay, going from 0 to 4. All right. And then we just got to integrate this thing. Don't forget your dx. All right. So we just got to integrate. Remember, we're adding one to the exponent, right? So it's going to be negative 2. We have an x cubed over 3 plus, and we're just adding one to the exponents, we have 8x squared over 2. Remember our power rule? So this is equal to 4x squared, this guy, minus 2/3 x cubed. Notice that when I've integrated, right, we added 1 to the power, this sign went away, all right? We've used it up. And we're going from 0 to 4, okay? So what we have here is we have 4 squared minus 2/3 4 cubed, all right? And then we have 4 squared is 16, and 16 times 4 is 64, minus 2/3 4 cubed is also 64. So if I factor out a 64 here, we have 1 minus 2/3. What is 1 minus 2/3, right? 3/3 minus 2/3 is 1/3. So we have 64 times 1/3 here, and our answer for this is 64 thirds. All right. So that is our answer for the area between these two curves. All right. So good. All right. Let's try one that's a little bit harder. I got this one out. You can see I got this one out of your book. All right. So what we have here is this is a sideways one, right? We have x equals e to the y. We have x equals x squared or y squared minus 2. All right. And in this case, it does tell us, like, we want to go between y equals +1 and y equals -1. So we don't have to figure out an intersection, thank goodness, because easier said than done here. All right. But that's how we're going to do this. So we know which one, right? We know this is the right. We know this is the left. So we're going to take this red one minus this blue one. All right. So what we're going to do is we're going to integrate from -1 to +1, okay, of e to the y minus, and in parentheses, y squared minus 2. All right. And that's how we have to set this thing up. All right. So dy, right, for the whole thing. So what was the integral of e to the y? It's the easiest integral anybody will ever ask you, isn't it? All right. And then we're going to have a minus y squared and a +2 here. So we have to integrate. What's the integral of y squared? Well, that's y cubed over 3. Okay. Plus, and then we're integrating +2. We just get 2y. And we're evaluating from -1 to +1. All right. So now we have to do the hard part, right? The integration, the calculus is actually not so bad. Now we have to do arithmetic. That's where it gets to be difficult. So the way I like to do this is I like to say, well, this is e to the 1 minus 1/3 plus 2 times 1. And this is y is evaluated at 1. Minus, okay, and let's put a -1 in here. We have e to the -1 minus, and we have -1 cubed here over 3. Okay, you got to be careful with signs. Plus 2 times -1. Okay, so let's go ahead and evaluate this part. This one, there's not a lot we can do with this, right? This is e to the 1 plus 2 minus 1/3. We'll come back to that. Minus, parentheses, e to the -1. -1 cubed, that's what? That's -1, isn't it? We have minus a negative, so we're going to have a positive 1/3 here. Okay, and then we have a -2. But don't forget this negative here. Okay, so we have here, we have e to the 1 plus 2 minus 1/3 minus e to the -1 minus 1/3 plus 2. Negative times negative. All right. So to sum this thing up, something feels like it shouldn't have. Yeah, okay, we're okay. So double check to make sure my little notes here are right. Yeah, we're okay. So we have e to the 1 minus e to the -1. 2 and 2 makes 4. And then we have 1/3 and 1/3, so minus 2/3. All right. So let's go ahead and combine our fractions, right? 4 is a fancy way to write 12 thirds. So we have 12 thirds minus 2 thirds. And that is equal to e to the 1. You can just write e. You could write 1 over e here if you really wanted to. And we have plus 4 minus 2 thirds, so this is a plus. So this is going to be a plus 10 thirds. All right, and that is our solution for this. All right, so that's what we have for that one. All right, now we're going to do one more. So notice that we started off pretty tame, right? So this one's pretty easy. This one's pretty straightforward. Okay, always a good warm-up question is to do the straightforward one. This one still pretty tame, except that a little twist in it where we had to, maybe turn it sideways and look at it kind of that way. And then we're going to talk to you about one that's a little bit harder. Okay. Now there is one very much like this in your homework. Okay. As a matter of fact, it's exactly where I got it from. But I wrote it this way because I copy and pasted this from a previous test. So I have given this problem before. So I just want you to know that this is the kind of thing that you're in for. Okay. So just let me warn you, not every problem has to be the hardest problem in the world though. Okay. So what are we doing here? It says consider the function 3 sine x and g is equal to 3 cosine 2x. And the first thing, and I try to, well, I can't do that in the online homework we have, the online things we have now. They do give you some hints regardless, but in a face-to-face class, I would have told you, like, hey, I want you to graph it first because you have to draw out your problem. And then note where your 2 points, where your 2 functions intersect, because we're going to be figuring out the area between these 2 things. So you have to know this. And then we're going to go ahead, sketch, and use your knowledge of calculus to determine the total area between these 2 functions on this interval. Okay, so how do we sketch this thing, right? So everybody who, if you remember taking trig and the graphing and skipping out on that and saying, why do I ever need to know that? Well, technically you could go ahead and use Desmos to do this. When you use lockdown browser, you won't be able to, but we'll call this pi over 2 because that's what we really care about. Okay, and what does sine look like? Right, sine looks like this, doesn't it? Where's the pi over 2? It's right there, right? So here's 3, all right? So here we are. Okay, pretend that hit the 3. All right, now what does cosine look like? Cosine, right, looks like this. That's how you can tell, right? If you take the derivative of cosine, right, it's got a negative sign, right? The derivative of cosine is equal to negative sine. And if you start looking at it where its slope is, right, it's got a negative slope when it first starts off. So that's a way to remember, like, oh yeah, cosine is negative sine. Because when you start to draw them, cosine falls off a cliff, right? Whereas sine is stuck climbing that cliff. So sine is a positive derivative. Derivative of sine is cosine. And then derivative of cosine has to be a negative one because we're falling. Okay, we're going down first. So here we are. Try to make that so it actually matches. And cosine negative 2x, or of 2x, right? This shrinks down what's going on here. So it's really something like that. Okay, so if we plug in 2 pi over 2 here into x, right, we actually get 2 times, we actually get pi. Remember, cosine of pi is down here, okay? So it's down at negative 3, all right? So if I plug in pi over 4, right? So if x were equal to pi over 4, 2 times pi over 4 is pi over 2, and that's where cosine is 0. So here's pi over 4. So what we're doing is we're coming down, okay, and that's going to pretend to be a cosine. Okay, So this is a tough problem now. It doesn't say bounded by. It says between x equals 0 and x equals pi over 2. So we have to go between these two functions, right? These two values. I want all of this area here. I want all of the area here. And then I want all of the area in this spot. But there's a problem because look, at the beginning, which function's on top? Function on top is the cosine. And then when we get to a certain point here, the function on top turns into the sine. So they're going to flip, all right? And we have to know like what's going on with that. How are we flipping this? So it might be useful to know where the heck do these two functions meet? Okay, what's going on here? So why don't we set them equal to each other? Why don't we say this is 3 sine x is equal to 3 cosine of 2x. Huh. Well, again, this is for all the people who, you guys took trig, and you said, oh, trig equations, I'll never see those again. Welcome to hell, because you're going to see these a lot. All right, so we have sine x is equal to cosine of 2x. Now, you can't solve this because, first off, the arguments are different, right? One's x, one's 2x. And the second thing is you got sine and you got cosine, and that ain't going to work. But you guys all remember your double angle formulas, right? Like it was yesterday, exactly. So we have 3 of them. This was 2 cosine squared x minus 1, 1 minus 2 sine squared x, okay? 1 minus 2 cosine squared, minus 2 sine x. And we also have cosine squared minus sine squared. Okay, those are your 3 options for cosine of 2x. Well, we have a sine x over here. Wouldn't it be nice if we could turn everything into sines? That's what we're going to do. Okay. By the way, I tease you guys about like memorizing this and having this like something that you should already know. Like I would just like, how would somebody not know this? Like I'm partly teasing you with this because I know it's been about a year since you've done this. I know it's been about a year since anybody's asked you about this. I will ask you a lot. Okay, so we're going to get practice doing all of this stuff. So I don't want you to look at this and say, oh my God, I don't remember this. I'm like, well, this is going to be your time to go back and learn some of this. Okay, so there we go. So we have that. All right, we got to solve this thing. So what are we going to do? We're going to say, well, we're going to use the AC method. So 2 times -1 is -2. I got to come up with 2 things that multiply out to -2, but add up to +1. How about use 2 and -1? 2 minus 1 is 1. 2 times -1 is -2. What we're going to do here is we're going to say this is 2 sine squared x plus 2 sine x minus sine x minus 1. You didn't believe us when we said, you know, this is all going to be part of a bigger problem. And if you're spending a lot of time, if this is a 20-minute problem for you, you're going to die of old age by the time you finish this problem. All right. Don't, you know, you got, if you're here where this is still a really slow process for you, you got some things to practice on. You've got some time to practice it. Okay. So it's not the end of the world. And no matter what it looks like right now, I guarantee you, after you've done a couple of these problems, all of this will start looking a lot easier. Okay, so this is not, don't look at this and panic and think, I don't belong here. Yes, you do. It is something you can overcome. It is something you can practice. You can get better at it. It will come. It may be, you know, it might take a while. And if this is all looking completely forward, you're like, oh, I remember this somewhere. Like, please go back and start working on some trig. Please go back and, you know, and get yourself familiar with doing problems like this, because there's going to be a lot of this stuff. All right. So we have sine x is equal to -1, or sine x is equal to 1/2. Is that okay? You guys are all right with me putting the 1 over here and then dividing by 2? Do you remember, right? Where is sine x equal to -1? Oh, that's down here, right? That would be down here. That's going to be, right, 3 pi over 2. So x is equal to 3 pi over 2. Okay, there was a couple other places too, right? We kept going. Okay, over here. It's going to be a lot of them. However, what interval do I care about? I care about between 0 and pi over 2. Well, 3 pi over 2 is way out of bounds. We don't care about this. Okay. Where is sine x equal to 1/2? That would be in here somewhere, right? That would be in here. So when sine x equals 1/2, right? Remember, sine is climbing. That's a small number, right? So it should be a small angle. So we're going to say, or x equals pi over 6. Again, this is all the radians. You can't use degrees here. Okay. So x is equal to pi over 6. Well, that is in my interval, right? Pi over 6 is somewhere between 0 and pi over 2. So that is the point of intersection. That's where they flip. Okay, so we've got 2 problems now. See how delightful this can be? So what we have here is we have the integral from 0 to pi over 6. Cosine was on top, right? Remember where we were on the problem. Cosine was on top at the beginning. So what we're going to say here is cosine of 2x minus sine x. But don't answer yet, because we also have the second part of this integral, because we only got to 0 to pi over 6. We got to get from pi over 6 to pi over 2. And that's when they flipped. All right, that's where they flipped. So now sine is on top, cosine's on the bottom. Okay. All right. So here's, you might want to think about like maybe how to streamline some of this at this point. I've got to integrate cosine 2x. I got to integrate sine. I got to do it twice. Could we just make a little thing off to the side here and talk about our indefinite integrals and what is the integral of sine x dx? Okay. We'll put a little a and b here. That way we remember we've got a definite integral on the way back here, but let's just go ahead and do that. And right, the integral of sine, right? Well, I always remember it the other way, right? The derivative of sine is cosine. So the derivative of cosine is negative sine. So if we put a little negative and a negative, right, we should be able to get this as negative cosine x, evaluated from a to b, or plus c if you're indefinite. Okay. And then what about cosine 2x? And this is why I did this, was because, you know, for some people, you might be looking at this thinking, piece of cake, too easy. Some of you might say, yeah, I remember doing this, but I'm going to need a little help to get through it. So what we're going to do is we're going to say let u is equal to 2x, and dx was equal to 2 dx. All right. So remember doing our substitutions here. So really we have the integral of UA to UB. There are some teachers that get really, really picky about this. I am not one of them. Okay. I try to show it to you so that way if you ever have to deal with this, you'll know, you know, the formality that people are using here. But if you just wrote A and B and you changed to U, like I'm not going to say anything because I know this is all shorthand and all to kind of sketch this out for you, and it's not coming here. Later on, we'll be formal. Okay, there's a section where we have to be real formal, but this is not it. Okay, so we've got, you know, let's start putting things into the U world here. So we've got cosine of U, right, and we have, instead of dx, right, we have, oops, this is du is equal to 2 dx. So du over 2 is equal to dx. When I substitute for my dx here, we've got du over 2. All right? So this is 1/2, right? Integral cosine u du. What is the integral of cosine? Well, the integral of cosine, right, is sine, right? So the integral of cosine is sine. Yeah, because the derivative of sine was going to, so that's going to go ahead and give us 1/2 sine of 2x. And now since we're back in the x world, we can go back to a and b. Okay, so we have a little cheat sheet here to say that the integral of sine x dx is equal to negative cosine x, and the integral of cosine of 2x was equal to 1/2 sine 2x. All right. So when I'm going back and looking at all of this, okay, I don't need to integrate 1, 2, 3, 4 things and deal with all of that. We've done it once. We can use our little cheat sheet here to just integrate these pieces. So the integral of cosine 2x, right, is, so our integral here. So, let's just go ahead and rewrite it. So we've got integral from 0 to pi over 6. What are we working on here? We've got cosine 2x minus sine x plus integral of pi over 6 to pi over 2, and that was sine x minus cosine 2x. All right. So when I integrate my cosine 2x, right, we've got 1/2 sine 2x. And then we integrate our sine here, we've got this minus, okay? And then we have a negative cosine x. Okay, we're evaluating this one from 0 to pi over 6. Let's just work on that. That seems like it's a hard enough problem as is. We'll come back to this one to do this arithmetic. Okay, so we've got 1/2 sine 2x plus cosine x, evaluating from 0 to pi over 6. If I plug pi over 6 in here, right, that's, oh, there's a 3, isn't there? I forgot all about my 3 way at the beginning here, because this is still 3's. This is still 3, because it's 3 times both of these, 3 times both of these. We don't need it for this, but there's a 3 like way out in the front here. Okay, so we've got 1/2. Go ahead, we've got all this going on here. Okay, we've got 3, and we've got 1/2. What is 2 times pi over 6? Isn't that pi over 3? So it's 2 times, or 1/2 times sine pi over 3 plus cosine pi over 6, right? This had different arguments, remember. Okay, minus, right? And then we're going to have 1/2 sine of 2 times 0, sine of 0, okay, plus cosine 0, right? And that's my first region here. We're going to do the same thing with the second region and do that arithmetic. All right, so we've got 3, and we've got 1/2. What is the sine of pi over 3? You guys remember that, right? It was square root of 3 over 2, wasn't it? So square root of 3 over 2, that is our sine of that. See, again, I know we told you in Schweik, like you're going to have to memorize these things. When you didn't believe us, now it's going to hurt. Okay, cosine of pi over 6, again, square root of 3 over 2, because again, cosine looks like that. Pi over 6 is over here somewhere, it's a big number. Minus, all right, oops, still parentheses, do that. Sine of 0, 0, cosine of 0, 1. Okay, don't, that's a tough one. So you have to remember cosine, right, again, looks something like this, cosine of 0, 1. Okay, so what do we have here? We have 3 square root of 3 over 4 plus 3 square root of 3 over 2. We could combine these. Bear with me for a minute. Minus 3. All right, we're just going to hold that aside. That is the region 1. Okay, that was from 0 to pi over 6. Now we got to deal with region 2. Okay, so again, right, we've got the integral here, right? So we just let me go ahead and do something like this. All right, let's get rid of this. I don't need that. And let's go ahead and do region 2. Green, is that better? Yeah, we'll do region 2 in green. Okay, so this was region 1 in blue, region 2 in green. So what is the integral of sine? That was negative cosine, right? That was negative cosine. And then minus, what was the integral of cosine 2x? And the integral of cosine 2x was 1/2 sine 2x, right? And again, we're going from pi over 6 to pi over 2. So let's see here. Actually, we could, really, am I that? Can I be clever? I think I can. Okay. Do you remember that if we swap the integration limits, we could change the signs? It was kind of a thing in Calc 1. You may have learned that, your teacher may have gone into that, but since it's easier to not deal with the signs, let's go ahead and say this is cosine x plus 1/2 sine 2x, and then we're going to go from pi over 2 to pi over 6, right? So if you swap the signs, if you swap the limits of integration, you can change these guys to positive. Okay, since they're both negative, they both turn to positive. If we had a mixed match sign, we would have to mix match. Okay, so in this case, I think this is a slightly easier way to go. Okay, well, we have cosine of pi over 6 plus 1/2 sine of 2 times pi over 6, right? And that we're going to have a minus cosine of, right, pi over 2 plus 1/2 sine of 2 times pi over 2. All right. Get down here, we'll have a little bit more room. I wasn't careful about that here. Okay. So we have plus, this is region 2, so we're still dealing with this. It's cosine of pi over 6. There's a 3 out in all of this. Okay. So pi over 6, that was square root of 3 over 2, wasn't it? Right? Plus 1/2. Right? Sine of pi over 3 is also square root of 3 over 2. Okay. And that's minus. Cosine of pi over 2 is 0. And 2's cancel, so sine of pi, also 0. So plus 0. So we have 3 root 3 over 2 plus 3 root 3 over 4. And this was my region 2. I'm off a sign somewhere, I think. Let me double check here. Oh no, we're still good. Okay, we're still good. So here what we have, right, is we have no, I think I am off a sign. Dang it. Where did the sign go? Derivative of sine is cosine, derivative of cosine is negative sine, so we're good there. Yeah. All right. Double check me on my signs here. So what do we have? We have 3 root 3 over 4 plus 3 root 3 over 2 plus 3 root 3 over 4 plus 3 root 3 over 2 minus 3. Okay, so region 1 plus region 2. And then here we have what? Square root of 3, we have 3 root 4, or 3 root 3 over 4, 3 root 3 over 4. That's going to be 6 root 3 over 4. We have 3 root 3 over 2 plus 3 root 3 over 2. So we have 6 root 3 over 2 minus 3. All right. So let's go ahead and make this times 2 to get common denominators. So we have 6 plus 12 root 3 all over 4 minus 3. And we can clean this up a little bit, right? We can cast out a 2 or something and make this 3 plus 6. Oops. Don't do that. Oh, I know. We could do it this way. We'll do this. There we go. Because they're both times root 3s. So we have 18 divided by 4. That's 9 halves. All right. So let's go ahead and the blue. So this whole thing is equal 9 halves root 3 minus 3. And there we go with our values there. Okay, so there we go. All right, there we go. So this problem is a very nice problem because it has you do everything that you've learned in pre-calc. Well, not everything, but it has you do a lot of stuff you learned in pre-calc and all of the fun stuff in calculus. So that's why I like this problem. Is it just gives you a lot to do from a lot of different places. Okay. When I would, again, we're on a computer. I don't know if I can really give you this problem as is because there's a lot of parts. And when I would grade this, you would get a little bit of credit for did you draw the function correctly? Did you find the points of intersection? And did you set up the integral? And how far did you get with that? So it was not that interested in you coming down with the absolute right answer, although now we're graded on computers, so we have that. But I was interested in all of the little moving parts that went up to this because you do this problem again, you'll probably verify that you got the right answer. That's a lot to ask for on a test. Okay, so I get that that's going to be a lot, but like I said, I broke it down and I would grade you on each of these different pieces so that you had a chance of getting a lot of credit just by doing this. And then if you made it through the integral, fantastic. But if you kind of messed up a little bit along the way, I was great. I used to grade out of 6 points. This would be a 5 out of 6 if you got these 2 parts and didn't get the rest of it. Okay, you screwed up a little bit, which was a B. Okay, so I don't want you to look at this and say, I have to get all of this right. No, it's definitely I've got to take parts of this down and break it up into sections so that you get a chance of getting a good grade, even if you made a minor mistake somewhere. So even if you made a mistake in here, right, that would be a -1, but maybe you did your integral right, and you'd still end up with a 5 out of 6. So if you screwed up any one point, nobody screws. Actually, I should lie. I'll say nobody screws this up, but I was wrong. So practice your trig. You'll get a lot of practice along the way. All right. So I'm going to stop there. I will tell you this is very similar to a problem in your homework. So you'll have at least one chance to practice this, and we'll stop there. Okay. Fill out your surveys. Make sure I know when to run the classes, and we'll go from there. All right. Thank you. Stopping and end.